would like to thank Dr. Wu for the kind introduction and invitation. It's my great honor to present our recent work here. So today I will introduce SINO, the Starter-Iterator Neural Operator for forward and inverse problems. The main idea is very simple. We first obtain a good initialization, a good initial approximation, and then we refine it step by step. This design is inspired by classical numerical methods, for both, but both parts are learned from data. My talk has 4 parts: operator learning, the SINO methods, application, and conclusions. I will first give a short background on physics-informed and data-driven operator learning. Then I will focus on the SINO architecture and show several forward and inverse applications. Many physical systems can be described by differential or integral equations. The first example is the time-dependent PDEs, and the second example is the Fredholm integral equation of the second kind, which is widely used to model the imaging precise. For example, the Ladon transform is also a kind of Fredholm integral equation. In operator learning, the goal is not to learn one particular solution. Instead, we learn mapping from the input function to an output function. In a forward problem, the physical model parameters and the source terms are given. The goal is to predict the solution field. For example, thermal conductivity and the heat function and the heat source determines the temperature field. Similarly,
maybe you need to turn to the next page. Yeah,
okay.
The slides still show the first page, the title page.
Title page. Okay.
So it's only SINO unified.
I skip and share again.
Okay, no problem. Okay. You can try to reshare.
Okay. How about this?
Yes, this is a phase.
Can we see the forward problem?
Yes, we can see.
Okay, so I continue. For the forward problem, our task is to use the physical model parameters and the source terms to predict the solution field. So this is the differential operator, and this is the source function. This is the solution field. For example, by using the thermal conductivity field and heat source, we can determine the temperature field. Similarly, medium property and excitation determines the wave field. So for the inverse problem, it goes in an opposite direction. We observe the system responses and try to recover the unknown parameters and structures. So this is we use the source and observe the responses to predict the system parameters. For example, the high resolution, we can recover the high resolution image in the super resolution microscopy, or recovering a hidden scene in the non-line of sight imaging. One important direction in physical is the physical informed learning. The network predicts the physical states, while the governing equation and the initial boundary conditions are enforced through the loss function. The main advantage is that physics can provide additional supervisions, so less data may be needed. However, many physics-informed models still require new optimization when the problem setting changes. The figure shows the basic physics-informed operator learning. The network, this neural network predicts the solution, and the automatic differentiation gives the required derivatives. The derivatives are inserted into the governing equation to form the PDE residue. The residue, together with data and boundary condition, initial condition, all these are used to train the network. Here, the physical, there are different ways to introduce the physical constraints. The deep race methods use an energy formulation. Physics-informed neural networks, the pins, directly use the PDE residue. And the gradient enhanced pins also introduce the derivative of the residue. On the other hand, deep finite volume methods is based on the local observation, based on the local conservation laws. The main difference is how the physical law is built into the training objective. Sampling is another important issue. Uniform sampling is simple, but it may span many points in the region that are already easy to learn. So adaptive methods use the current residues or errors to place more samples in the difficult regions. This can improve both training efficiency and accuracy. Network architecture is also studied for physical informed learnings. Methods such as the examples include GANs, CNNs, recurrent networks, transformers, and CANs. These architectures provides different ways to model spatial structure, temporal dynamics, and nonlinear behaviors. Feature embedding is another way to improve the physics-informed learning. Fourier, for example, Fourier feature embedding, prior dictionaries, neural tangent kernels, and dimension augmentation can enrich the feature representation. However, the model still solve individual problem instances and usually need retraining when the condition changes. This motivates learning the solution operator directly. This leads to the data-driven neural operator. A neural operator, for this case, the neural operator learns the mapping from the input functions to the such as the coefficient and the source field to the solution field. Training minimizes the data mismatch between the predicted and observed fields. Usually, the squared L2 error is used here. Once trained, the operator can predict new solutions directly without solving the PDE again. DeepNet is a representative of neural operator based on the branch trunk structure. The branch net maps the input function to the coefficient, and the trunk net maps the query coordinate to learn the basis-like function. Then the inner products of the coefficient and basis function gives the final output. Extensions include MIO-NET for the multiple input operators, ResNet-based DeepNet for complex geometries, and the sequential DeepNet for sequentially for sequential predictions. This slide shows two depot net architectures. The stacked depot net use separate branch net, while the unstacked depot net use one branch net. In both cases, the trunk function are learned freely from the data. So linear dependence, completeness, and numerical stabilities are not guaranteed. As a result, the representation can become redundant or ill-posed, making the coefficient less interpretability, and the approximation is less stable. Another idea is to use fixed basis function. FNO is the best known examples, using Fourier modes to represent functions in the frequency domain. Related neural operators also includes the wavelet neural operator, which use wavelet basis. Laplace neural operator employs the Laplace kernel function, and the spatial neural operator, which use the Chebyshev basis. This figure shows the basic FNO architecture. FNO transforms the feature to the Fourier domain, applies the learnable spectral weights, and then transform them back. So this is this branch. In the Fourier domain, we learn the spectral weights for each mode and then combine together to send them back. For efficiency, only a limited number of Fourier modes are usually returned. Therefore, the mode truncation may lead to the loss of high frequency information, which is also one motivation of our SINO. Now I come to the main methods. Many forward and inverse problem can be written after discretization in the form of AU equals F, where A denotes the differential or integral operator, U is the solution field, and F is the source of all observations. Classical iterative methods can be used to solve these linear systems. It usually starts from an initial guess and progressively reduce the error through repeatedly correction. A good initial guess can make the later iteration much easier. So our SINO follow the same idea. First, initialize the solution and then refine the remaining error. This theorem gives the spectral motivations. For the stational iteration considered here, high-frequency error components decay faster, while low-frequency components decay more slowly. So classical iteration tends to remove high-frequency error first. This suggests us a complementary design. The starter captures the low-frequency structure, while the iterator focuses on the remaining residue. Based on this idea, SINO has two basic modelers. The starter gives an initial approximation in the lifted feature space. The iterator then refines the residue step by step. The two modelers have different rules, but both of them are parameterized using the neural networks. Now we look into the starter operator and the iterator operator. For the starter iterator, it is designed as a learnable low frequency initializer. It transforms the input to the Fourier domain. And we keep selected the low modes and apply learnable spectral weights. So this is the weights we are going to learn by the neural network. After the inverse transform, we also introduce a pointwise linear path. The goal is to provide a stable global approximation before the iterative refinement. The iterator is obtained by deep unrolling of a classical iterative scheme. Each iteration becomes one network stage. At each stage, one learned operator, A theta, forms a residual-like term. The dk is the residual-like term, and then another operator B theta map this term to a correction to the current solution. So this is the final update of UK. Repeating this stage progressively refines the prediction. So we update this U by n times and get the final estimate of the iterator operator. This figure shows the full SINO pipeline from the input lifting through multi-skill processing to the final projection. The lifted feature are processed at several resolutions. Restriction this green line denotes the restriction. Restriction creates coarser representations. At each scale, it has its own starter modular and iterator modular. This is the detailed structure of the starter operator and iterator operator. The coarse output is then prolongated and concatenated to with the feature at the next final scale. Finally, we use the projection operation to output the prediction. We also studied the approximation property of SINO. Under the assumptions shown here, the theorem states that SINO can approximate the target continuous solution operator arbitrarily well on a compact set. The main point here is that the starter iterator decomposition does not remove the basic approximation capability of the neural operator. Here, I will not go into the proof. The previous theorem described the spectral behavior of the iterative solvers. Here, we study the spectral bias of the network itself using a one-dimensional Poisson equation. Here we use different initializations. From the result, we can see even when the high frequency components are included in the initialization, the network still first fit the low frequency part. Therefore, the low frequency initialization also reach a lower loss faster, indicating the faster convergence. So the first column is the initialization with low frequency, and the fourth column is the initialization with high frequency. You can see the low frequency one converges faster as the approach goes. So this result support our choice of a low frequency starter. With the SINO architecture established, I will now move to the applications, starting with the forward PDE prediction. We evaluate SINO on 3 time-dependent PDEs: Navier-Stokes, acoustic wave, and shallow water. These problems have different dynamics, and we also vary parameters such as viscosity, source, and wave speed. The model predicts the next state from the current state and the problem parameters. For long-term forecasting, this one-step operator is applied repeatedly, so error accumulation is an important test. This table compares the one-step error predicted across the 3 PDE problems. DeepNet, as can be seen, DeepNet has relatively large errors, while FNO and MGNO give much stronger result. SINO further improves on these baselines and achieves the lowest error in all 5 settings. Compared with the baselines, SINO stays closer to the ground truth, especially for the Navier-Stokes equation at low viscosity, which is a more challenging case. This is the higher viscosity Navier-Stokes case. The length operator is applied repeatedly for long-term predictions. Compared with the baselines, SINO stay closer to the ground truth. So we can see the residue image. The SINO stays closer to the ground truth and better preserve the main flow pattern over times. This is the low viscosity Navier-Stokes case. So the flow contains finer structures, so the prediction is more difficult. The difference becomes more visible at later time steps, and the SINO still gives more stable long-term results. So the residue is visibly small. This slide shows the acoustic wave problem with variable source. Wave propagation is sensitive to phase error, so small prediction errors can grow quickly over time. SINO better preserves the propagation pattern during repeated predictions. This ablation study evaluates the starter. The S denotes the starter, iterator, and the multi-scale design. The full model performs best at every time step and show the largest improvement. At t equals 50, the error is reduced. The error is reduced from 10 to -2 level to below 10 to -3, which shows much less long-term error accumulation. We also studied the initialization and the skill setting on the Darcy equation. The left plot shows the learned starter converges faster than the random and zero initialization. And the red plot compares different skill settings. It shows that the benefit of the multi-skill design. This result support both the learned initialization and the multi-skill architecture. Now I move to an inverse problem, the super-resolution microscopy. The goal is to achieve spatial resolution beyond the diffraction limit. and reveal very small tubular cellular structures. Different super resolution microscopy techniques achieved this in different ways, but a higher spatial resolution often comes with lower temporal resolution. So we study the computational reconstruction methods from low resolution observations to improve the scanning efficiency. The forward imaging model is simple. Here, the low resolution image is obtained by convolving the high resolution image by the point spread function, and then adding a noise function. So the inverse problem is to recover the high resolution image from the blurry and noisy observations. Existing methods include both model-based and learning-based approaches. Sparse deconvolution methods use explicit priors such as the sparsity and the smoothness priors. RCAN and DFCAN learns the reconstruction from data, especially the DFCAN also use the frequency domain information. Actually, there are limitations for both model-based methods and learning-based methods. For model-based approaches, they are usually sensitive to noise and the PSF errors, while learning-based methods usually require more data and have less physical interpretability. For the experiments, we learn the mapping from the low resolution image to super resolved image. We use the BioSR dataset, which contains 2,200 paired images from structured illumination microscopy. The dataset contains 4 cellular types: the CCPS, ER, microtubulars, and F-actin. These structures have different levels of complexities, which give a useful test of reconstruction quality. This is the visual construction results on the BioSR. From top to bottom, the structure becomes more complex. We can see that SINO produces a result similar to the ground truth, especially for the microtubulars and the F-actin. The arrow maps also show the same trend. This page gives a more quantitative quantitative comparisons. The intensity profiles at the top row show the signal follows the ground truth more closely. Here, the ground truth is the black line, and the signal is the red dashed line. The box plot on the box plot shows the PSNR value. It also shows that the signal gives much higher PSNRs on all 4 structures. So the improvement is consistent across structures with different complexities. Our third application is the weather forecasting. Numerical weather prediction forecast the future state of atmosphere by numerically solving the governing PDEs of atmospheric dynamics and thermodynamics. As shown in this figure, many physics processes interact across different spatial and temporal scales. As a result, high-resolution numerical forecasting is computationally expensive. The standard numerical weather prediction has 4 main stages: the data acquisition, data assimilation, numerical integration, and the post-processing and evaluation. The data assimilation combines combines the observation with a model state to estimate the initial atmospheric condition. The numerical integration then advances the governing equation in time. This integration step is one of the main computational costs. There are primitive equations for large-scale atmospheric dynamics. They describe the momentum, the momentum, the hydrostatic balance, continuity, and aerodynamic energy. The equations, as can be seen, the equations are nonlinear, strongly coupled, and involve many atmospheric variables. So this makes full atmospheric prediction a very challenging high-dimensional problem. Recent deep learning weather models include forecast.net, graph.cast, Pangu weather, and Fuxi has been established for weather prediction. These models use different architectures, including the Fourier neural operator, the graph neural networks, and the transformer-based architectures. These studies show that the strong potential of data-driven weather prediction. Here we use a simple temperature prediction problem to test our SINO. To reduce the problem complexity, we focus only on the 2-meter air temperature prediction. The data are regraded to 128 by 64. The learned model is applied repeatedly to obtain longer forecasts. Here is the result. We train our model on data from 2010 to 2016, and validate the model using 2017. We then tested it over the year 2018. Here the red curve denotes the SINO, and the black curve is the baseline model. We can see the SINO gives lower and more stable prediction loss, showing good potential for long-term predictions. Now let me summarize the main points. The Starter-Operator captures the low frequency information and provide stable initialization for long-term forecasting. The deeply enrolled iterator operator then refines the remaining residue step by step. Together with the multi-skills design, the same framework works for forward PDE prediction, inverse imaging, and long-term dynamical prediction. So our future work will focus on more complex and coupled multi-physics systems. This figure shows the broad range of neural operator applications. The same operator learning idea can be used for both forward and inverse problems in fluid mechanics, imaging, and many other fields. This is why we believe neural operator provide useful common frameworks for scientific computing. This is the end of my talk. Thank you for your attention, and thanks to all my collaborators.